Okay, I guess we can start. Okay, so today is the first lecture in the sequence, the Landau lectures that are given here every year. In fact, it's, I think, the only sequence that we have which is in general mathematics and not just in the mathematical discipline. As far as I found, I hope that's correct, the Landau lecture started in 1992. The first lecture was Jürgen Moser, and they were very distinguished mathematicians who gave the Landau lectures over the years. One of them is Bill Thurston, who was Yair, our speaker today, advisor. Actually, that's the first Landau lecture that I remember. It was in my first year here as a faculty in 1996. Okay, I'll say something about a few things only about Landau. Then I'll introduce Yair. So Edmund Landau was one of the founders of the institute. He came in 1925 when the university was founded, but came to actually stay here in 1927. And after a few years, actually went back to well, actually then he was in Göttingen. He was one of the leaders of analytic number theory then in the world, and in some sense he made his field be not only a bunch of results, but actually made it more systematic branch of mathematics. He was born in 1877, died in 1938. He was born in Berlin, died in Berlin, and he was a professor, as I just said, in Göttingen from 1909 until 1934, and actually he was thrown out of Berlin because of the Nazis came to power, and in fact the main person who was active in pushing him out was Teichmuller. That's also the lecture today somehow connected to his work. He was a Nazi, of course. Okay, but this is okay. Okay. So that's what I'll say about Landau. If you want, you can, because it's not difficult to find materials about him on the web today or here in the library. Our speaker today is Yair Minsky. He's a professor at Yale. Yair got his PhD from, or under the supervision of Bill Thurston in Princeton in 1989. He was a professor in Stony Brook, and then at Yale. I'll say only a few things about his mathematics, because I'm afraid that what I'm going to say will not say much to many of you, but his talk today will clarify some of these things. So I think he's best known for for several major works. One of them is the ending lamination conjecture, which was a conjecture of Bill Thurston, and somehow, in some sense, this conjecture completes, completes maybe is the right word, Moser rigidity, which is Moser rigidity says that there is a unique, essentially geometric structure on closed it's more general than that, but in particular hyperbolic three manifold, and the Thurston conjecture, the ending lamination conjecture, somehow classify all the geometric structures on manifolds that may have boundary. And there are infinitely many of them, and the ending lamination give parameters that somehow unify, somehow classify them all. And let me mention just one other major work of Yair, which was used in this work, but it has a lot of influence on actually more than one mathematical branch. And this is his work on the curve complex. This curve complex is something that one can associate with the surface, and the work of Yair and Howie Mazur is now fundamental in studying structures, hyperbolic structure on surfaces, and actually has influence on low-dimensional topology and on geometric group theory. Yeah, okay, I think I'll stop here. There's a lot more to say, but I'll leave the stage to Yair.
Okay, thank you very much for the invitation. I think actually I started learning mathematics here as a first-year student, so I always feel very good to come back. So I wanted to say, and the fact that my advisor gave a talk here about some of these ideas 30 years ago, so I hope that everyone went to his talk 30 years ago, and so I can just start where he left off. Yeah. So, yeah, so, yeah, it probably is. But so this first talk is going to be kind of a retrospective talk about some ideas in mathematics that start with Thurston to some extent, and I wanted to give you walk you through them in a sort of loose way. So I'm not going to surprise anyone who's any experts in the audience for the first talk. I'm hoping that some of it will set the stage for talks 2 and 3. The last thing I wanted to say was about Landau and Teichmüller. So thank you for mentioning Teichmüller. I think it's important to remember that Teichmüller was both a Nazi and a very good mathematician. He proved an important theorem that started the entire field of Teichmüller theory. It's important to know that somebody who does good mathematics does not have to be a good person, and vice versa. So I try to remind, I think it's one of these things, one needs to remember this thing, not to try to put it under some kind of rock. It's important. Okay. And please ask me questions through the talk. Do I have an hour or 15 minutes? Or no? Oh, the mic. I didn't do anything with the mic. How about now? It doesn't make any difference? There's a green light. Now you can hear me? Okay, good. Okay, so what I want to talk about is the notion of laminations. And how they connect to various ideas in topology and geometry, mostly in low dimensions. And in fact, much of the talk will be in dimension 2, but I'll try to kind of explain. Dimension 2 is very, very special for this set of ideas. I'll try to give a feeling for why that's true and say a little bit about what some things in higher dimensions, a little bit. So let's start with the definition. So let M be an n-dimensional manifold. A lamination of dimension D in M is a closed subset, lambda in M, but not just the closed subset, it's equipped with special coordinate charts. So these are coordinate chart in the usual sense. If you take an open subset of the manifold and you take a chart to Rn, and I want Rn, I want to think of it as Rd cross Rn minus D. And then I want, what's the cleanest way to do this? Maybe I'll say that the image, so phi of u, should be a rectangle, and phi inverse of, I guess I'm writing it this way, and phi of lambda intersect u will be a set of the form, which way do I want this? I guess I want some rectangle of dimension D cross some set K of that lives in the other n minus D factors. So I don't want to, okay, this is a little more formal than I usually like to be, but the picture you should have looks like this. You have some manifold, M, and then there's this set, lambda. And if you look at the coordinate chart, if U is here, the coordinate chart maps this to a rectangle so that there's some set, this is where I should have a color. The image of lambda in here should look like a nice product, where this is a set K here, and then this is just the full rectangle of dimension D. Is that clear as a definition? Yeah. K, in the general definition, K is just any closed subset of K in Rn minus D is closed. It's in a it's in a rectangle. So I guess here there's a rectangle of dimension D, and there's another rectangle of dimension n minus D. Okay? Okay, and K is any closed subset inside the vertical direction. And then I guess I should say what the transition maps I guess are constant, well, let's see, or the form x, y goes to, the height of the image only depends on the height of the in the domain. And what that means is that if I took two different coordinate charts living in part of the manifold instead of the whole manifold, okay? Any questions about this? Okay, so that's a lamination. I want to think about this for most of the discussion. N will be 2 and D will be 1, but I will loosen up a little bit later. But in particular, if so this is a very general sort of object. We don't want to talk about the most general situation. What I actually want is to capture something about, I want M to be a geometric manifold, and I want the lamination to carry useful information about the geometry. So I'm going to define a more specific notion. So if D equals 1 and the leaves of lambda are geodesics, so I should say if D equals 1, if M is Riemannian, so M has a Riemannian metric, and the leaves are geodesics. So the leaves are whatever maps to the horizontal red lines. Those are the leaves. Okay. Then we call this a geodesic lamination. Okay. Okay, and like much of topology, the local structure is not so exciting. I guess K could be an interesting set, but overall it's kind of a product structure that's not super exciting. But what's really interesting is what the global structure is. So the picture you should have in your mind is something like this. So I'm going to draw the case of a surface M, and the lamination is globally, it's some kind of complicated set, which is sort of filled out by leaves. So anyway, I always run into trouble drawing this because you never know where to stop or when to stop. But anyway. So you can imagine that such an object can be very complicated. Okay? What do I get by calling it, by restricting attention to geodesic laminations? I have other ways of describing what's going on. So let's be more specific. Suppose that, let M be a hyperbolic surface. So what does that mean? That means that M can be, that means there's two ways of saying what a hyperbolic surface is. You can say it's a Riemannian, so the definition 1 would be it's Riemannian 2-manifold with curvature, with constant negative curvature. Let's say curvature equal to -1 at every point. Okay, that's a hyperbolic surface. Another way to say this is that it's the quotient of the hyperbolic plane. So another way to get such a manifold is to start with a discrete subgroup of PSL2R, which is the orientation preserving isometry group of the hyperbolic plane. And I want gamma to be discrete and torsion free. And then I want M to be H2 mod gamma. Okay, so the picture you should have for this is one of these sort of Escher style pictures. This is a picture of the hyperbolic plane. And it has a metric which has constant negative curvature. And then inside of it, imagine there's a group acting. And maybe there's some fundamental domain that looks like something. I don't know, maybe some polygon. And then the group takes this and moves it all around. I'll just try to... Okay, I'm not going to try to draw the whole picture, but there's some group which acts on the whole plane. And if you mod out by the action of the group, it's like taking the fundamental domain, gluing the edges together in some way, and getting a surface out of it. Okay, I hope that's reasonably familiar. I allow cusps, yeah. I mean, in terms of definitions, you can allow cusps, you can allow a lot of things. It gets more, things get a little bit tighter and more interesting when you have surfaces of finite area. I mean, you still can allow cusps, or you can talk about closed surfaces. Okay, suppose that, but anyway, if I have any hyperbolic surface, then I can look at if lambda in M is a geodesic lamination, then its pre-image, let's write the map from H2 to M. Let's give that a name, pi. That's the quotient map. So if I look at pi inverse of lambda in the hyperbolic plane, it's also a geodesic lamination. It's not hard to see that if you take a geodesic lamination, the way I defined it, and lift it to a cover, it still is the same kind of object. So we can try to draw what it looks like. Maybe I'll draw it here. So in the surface, I had this local structure where the red lines are geodesic lines, which means that in the lift, they also have to be geodesic lines, because the action was by isometry. And so I get some kind of picture that looks like this. I get the geodesic lines have to be complete geodesics because they never stop, right? There's no end point to one of these things. That's part of the definition. They always look like this. So every geodesic, I can just follow it all the way, and it becomes a complete geodesic. So there's some kind of picture like this, which has to be invariant by the group. Okay, because it was a lift. Okay, and this gives me one more different sort of definition. So I want to, part of the point of this introduction is kind of, is to see that you can see these objects in several different ways, and it's kind of instructive to do that. So, right. So once I draw it like this, I notice the following thing. Geodesics in H2 are uniquely determined by their endpoints By the way, I'm assuming people have seen the hyperbolic plane at some point, and I hope that's a reasonable assumption. If not, you can consider this to be a bunch of stuff about the hyperbolic plane that you now know. Okay. Okay, so every one of these red geodesics had two endpoints on the circle at infinity, and it's uniquely determined by those endpoints. And therefore, I can determine, maybe I'll give this a shorter name. Let's call this lambda tilde. So lambda tilde is determined by the collection of endpoints, some set of endpoints, which lives in the circle at infinity, cross the circle at infinity. Okay? Right, so for every red line, there's two endpoints, so there's some closed set. Well, actually, I have to remove something. I have to remove the diagonal. Delta is the set of points p comma p. So every geodesic has two distinct endpoints, and so these are pairs of distinct endpoints. And actually, if I'm being super careful, I should really mod out by this z mod 2 action, which interchanges the two factors. And then this is really where the set of geodesics lies. So this is determined by this thing, E, which is a closed subset. Well, what you mean, can I
for example, you compare instead of telling a close to even, you can compare to odd to one before or something.
Oh, but there is no one before actually. So the set of lines here does not have to be countable or locally finite. So it's.
But the one with this,
Do you mean when you say the next one? Do you mean using the additive structure of the real line? Is that
take a point, a red point from the boundaries,
yes?
and connect it to the next red point, not the one before.
So maybe you mean
But then it's they give you also maybe something.
well, there are many laminations. So actually, maybe you're making me draw this picture. I think here's the hyperbolic plane again with the circle at infinity is the real line and the point at infinity, and I could put I could take all the integer points on the real line. I think that's what I want to do. Yeah, and then I could join each one to the next one. There's a unique geodesic that does that. Is that what you had in mind? Who said? Where were you? I lost where you were. Oh. I don't know if that's what you wanted. That's a picture I could draw. This one is invariant by the z action on the plane.
But some geodesics will not be lines from some. You can take the one 0 and 1.
Yeah, I didn't take. So this is some subset. It's not every pair. Yeah. So the set. Yeah, there's some set of lines which corresponds to some set of pairs of endpoints.
I agree, but the set is determined by the set of endpoints. Should give you the set of endpoints.
No, it's determined by the set of pairs of endpoints. It's determined by a subset of the product, S1 cross S1. So then, yeah, I see what you mean. So I'm not allowed to join. I keep track of the point and the other point. So I only join those two. I don't join this point to this point. That was your question. Okay. Right. That's why I need to think of it here in the set of pairs. Okay. So I have this thing. It's closed. It's gamma invariant. And it has one more special property, which is that it's I'm going to call it non-linking. So property. So what is this property? This property is the following property, that if you take two pairs of points in the circle, there are two ways. So here's a point and here's a point. That's a pair. Thank you for the colored chalk. And here's another pair. So this pair and this pair are linked in the sense that the blue points separate the red points and the red points separate the blue points. Okay. This does not happen. So this is not allowed. And the reason it's not allowed is that if I tried to join these by geodesics, they would cross in the middle. And there's never such a picture, right? Like in my drawing, where's my red? Right? If these two were joined, they'd have to cross. My lamination never has a local picture that looks like this because the definition was that it always looks like that. So there are no crossings, and therefore, on the level of the endpoints, there are no links between pairs of endpoints. Okay, so now I have a different description of what a geodesic lamination is. It's a closed set of pairs with this, which is invariant and has this non-linking property. Okay, and I guess. So I want you to keep this in mind because one of the things I kind of want to address is why, if I lifted this property, what do I get? Maybe I get something interesting. So once I've written down the property, I should think about what happens when I remove it. Okay, so keep that in mind too. We'll see why it actually comes up naturally. Okay. All right, so this is a different way of thinking about what these laminations are. And it gives us a nice consequence.
Such a set even, it will define a lamination more gamma for this particular gamma.
Exactly. That's right. It's an if and only if. So it's a bijection between objects like this and objects like that. Yeah.
Isn't the gamma action usually a pro? You have invariance?
Well, first of all, I didn't put a measure in yet, although it's part of the story to think about measures. But so sometimes these things support measures, and sometimes the action's ergodic, and sometimes it's not. Yeah, it's. One should have. Okay, maybe. I've gone a long time without any examples, so let's write down a couple of examples. Well, maybe this is kind of the most basic example. Suppose I take my hyperbolic surface and I just draw one single closed geodesic. So there are many closed geodesics, but if I pick a closed geodesic without any self-intersections, there are many of those. That's a lamination, and then here there's just a discrete set of lifts, right? What the pre-image of this lamination is. So this is lambda, and this is lambda tilde, and so what are these lines that I'm drawing? I mean, they're the lifts of this circle, but they are also the axes of the group elements that correspond to this loop in the surface. So all of these, the action of the group has various each of these lines has a stabilizer which translates the line. So the quotient is this loop, and the group. So this is a countable, and the action is transitive. So it is ergodic in this case. No matter, I mean, there's only one thing. However, I could draw one more circle somewhere that's disjoint from the first. That's still a lamination. Yeah. Sorry, the action of gamma. Yeah, gamma on E. E is countable. E is just a countable set of pairs of points, and gamma is just permuting it. It's acting transitive. On the other hand, if I had two of them, then they would lift, somewhere. I don't know. There'd be another bunch of. Anyway, there's some other countable collection, and the whole thing together, the union of red-blue, is acted on in the same but by gamma. But the action then would be no longer transitive. There's a red orbit and a blue orbit. It's no longer ergodic. Okay, so that's kind of a trivial example where it's not ergodic. Okay. Okay, and these are not the most interesting laminations, but they're very important. Okay, so where was I going to go? Well, a consequence of this part of the discussion is that if I change, so the hyperbolic, if I start with a topological, so the set of hyperbolic metrics on a given topological surface is not a single one. There's typically an infinite family. In particular, it's possible for there to be different groups gamma that are isomorphic to each other, which act in a conjugate way on the plane. So there are many hyperbolic metrics on a given topological surface, and this description gives a bijection between, let's write it as, suppose I write geodesic laminations on one surface X. So think of X as, think that you have a particular topological surface M, and it has two different hyperbolic metrics. Maybe we'll call one of them X. I'll kind of try to emphasize that they're different shapes. So I'll draw one like this, and then I'll draw the other one like that, maybe. Right, two different hyperbolic shapes for the same topological surface. Each of them can have their own geodesic laminations. Each of them corresponds to a different group acting, gamma X and gamma Y. But both groups are isomorphic. They're both the fundamental group of M. And in this case, sorry, I didn't finish the sentence. The description gives a bijection between the geodesic lamination on X and the geodesic laminations on Y, if Y and X are two hyperbolic structures on the same surface. And the reason is that the actions of the groups are two different actions, but gamma X and gamma Y, under this circumstance, have conjugate actions on the circle, topologically conjugate. So there's some kind of homeomorphism between, so here gamma X is acting on the circle, and here gamma Y is acting on the circle. And so if you take a pair of points on this circle, and you move it by the conjugating map, you get another pair of points. So the set of endpoints of one lamination here are just taken naturally to a set of endpoints of a different lamination here. So it's a bijection between the two sets of laminations. So we can think of, even though we call them geodesic laminations, and they depend in their definition on a hyperbolic metric, they are in some sense topological objects. Because when you change the metric, you naturally have a natural homeomorphism, natural bijection at least at this point, between the two different sets of laminations. Okay, so they become these kind of general objects that really capture something about the topology of the surface. Okay, the other thing I wanted to say about this, there's another point of view to this story, which is to relate the surface to the geodesic flow on the surface. So if M is a hyperbolic surface, then you can look at T1M is the unit tangent bundle. So the reason I'm talking about this is because it's a little bit more amenable to the point of view of dynamics, which I assume some of the people in the room have. So if you look at the unit tangent bundle of a surface, that's, in other words, it's a three-dimensional manifold consisting of all the unit length vectors that are tangent to points in the surface, right? At every point, there's a circle of unit length vectors. So this is, there's a fiber bundle, T1M to M, whose fibers are circles, namely the unit circle of the points. Everybody okay with that? Okay. And then this has a geodesic flow. I hope Ol doesn't mind if I don't write the matrix down. It's just this picture. If you start with a vector in the surface, because there's a Riemannian metric, there's a unique way to flow forward along a geodesic. If you flow forward at some particular amount of time at unit speed, you end up with a different unit vector, and as you keep flowing forward, you get lots of different vectors. So the flow line of a given vector is just the geodesic emanating from that vector in both directions. You should include both directions. So there's these geodesics in the surface, which correspond to flow lines of the geodesic flow. And the lamination, and you can talk about you can talk about the laminations corresponding to this flow in the three-manifold T1 of M. So So if you're interested in dynamics, you could consider flow invariant closed subsets of the unit tangent bundle, which is a three-dimensional manifold. Whoops, my M got sideways. Right, you have flow invariant closed subsets. So in this three-manifold, you're seeing, a bunch of flow lines. They're all disjoint because it's a flow. And so they make a lamination. You should convince yourself that if I take a closed flow invariant subset, it is in fact a lamination according to the first definition. And then they project, if I look at this projection from the tangent bundle to the manifold, I could start with some, let's give it some, I don't know, let's call it G, a flow invariant closed subset of this, and I could push it down here and ask what I get, right? I'll get something. Could be kind of very complicated, but I want to say that if the projection, if P from G down into M is injective, the image is a geodesic lamination. In M. Because what's going on here, how does it not be injective if you look at the picture down in M? So upstairs in this flow space, you had a bunch of geodesics. If you push a geodesic down into the surface, that means just forget the tangent vectors and look at the points themselves. Then you see that it might intersect itself many times, right? So this is, so here's a self-intersecting geodesic. That's not a lamination, but if it was, okay, so, and that's because the map is not injective over that point. But if it is injective, you get a lamination. Okay? So, so if you're doing dynamics in this homogeneous space here, then the natural object is just these invariant subsets.
What is G?
G is a flow invariant subset. Sorry, I should call it. Let's call it. G is one of these flow invariant subsets. Okay? So they are laminations upstairs by the first definition. But when you push it downstairs, for them to be a lamination downstairs, you need the map to be injective. Okay? And so you could ask yourself, so this is kind of related to the non-linking property, right? So in general, you'll get something, which if you draw it here, you'll get a bunch of geodesics that do have the linking, that do link. And then you should say, I should think about those because they naturally come up in dynamics. Okay, right? So, no. Let's see. Let me be careful about this. So this is not in the universal cover, but it's actually in the tangent bundle of the original. So if I had, so the picture is never injective from the universal cover into the surface. But if the picture sort of looks like this maybe. If I have a closed geodesic here without self-intersections, then up in the tangent bundle, it's hard to draw the tangent bundle. The tangent bundle is three-dimensional, right? It's also closed, right? I take these things and I push them down, right? So this is a picture where, so upstairs there's a circle of vectors which maps exactly to this, and it is injective. Now it is true, the if is, it's possible, I could have taken two things. I could have taken these vectors and also their antipodal vectors that point the other way. And those have the same, so then upstairs I would get two loops that map to the same loop. And that's a technical point. I have to think about that too. But if the map is injective, I definitely get a geodesic lamination. Okay. All right, so I want to say something about where these things come up. And why, so, let's see, what do I want to, I want to be able to ask the following question. First of all, why do these kinds of things come up in a natural way in the study of low-dimensional geometry? How do they come up? And what about the way they come up makes them into laminations as opposed to these general objects with self-intersections? What is it that makes things laminations? So I kind of want to focus on three different ways. So how do laminations arise? So these are all interrelated, but I want to focus on a couple of different types. So the first way is through, they kind of encode asymptotic behavior in various ways. And I'll say that's I'll talk about it in a second, but of geometric structures. Maybe I'll just write it that way. Two, they provide families of deformations. And three, they arise in geometric optimization problems. Okay, so I want to try to talk about each of these three things. How much time do I have, actually? 15? 10, what? What? 17 minutes, okay. Okay. Oh, actually, before I talk about these, I have to do one more thing. Maybe. What? 20 minutes. Oh, okay. All right. That was a very quick negotiation. Okay. Before I give little samples of these 3 points, let me kind of add one more ingredient, which is the notion of transverse measures, just so I can talk about it. So if you think about it from the point of view of these flows on the tangent bundle, once you have a flow, you can ask, are there any invariant measures for the flow? So an invariant measure for the flow, well, I'm not going to say what it is in words. The picture is this, right? You have a flow. I want to be able to say, there's a measure. So if you take a little piece of the space and you push it by the flow, the measure should be invariant. It should go to the, right? So in particular, because the flow preserves this arc length along the geodesic lines, an invariant measure has to look like in a small neighborhood. So the flow space looks like this kind of lamination picture. There's the flow direction, and there's in our case, a two-dimensional transverse direction, because the bundle is three-dimensional. So a flow it's the measure of, let's call this thing a box, right? The measure of a box should basically look like some kind of measure on the transversal part. So maybe we'll call it the transversal part. Cross I'll just write it as dl. This is arc length. Right? It has to look like that because it's invariant by the flow. And so somehow we know what this is always going to be. So this thing we could think of as a measure on transversals to the flow, and it should be invariant, under the flow. So if you choose a different transversal, you'll get a corresponding measure. And then if you push all this down by the map P into the surface, and you have a lamination, then, yuck. Okay. Then somehow these transversals in the flow space kind of give you transversal arcs to the lamination in the surface, and this kind of invariant measure gives rise here in the surface to measures on transversal arcs, and that's what Thurston called the transverse measure on a lamination. And it has to be again invariant under moving along the lamination. So that's what a transverse measure is. So I can think of not just laminations, but laminations equipped with these transverse measures. So I can think about, let's call it ML of M is measured geodesic laminations. So in other words, it's one of these objects I already discussed, equipped with a transverse measure, with a tiny, there's a technical point, which is that there could be little bits of the lamination that have zero measure. And you kind of don't want, in this space, you want to identify things if their measures are really the same. So it's a slight quotient of what I talked about before that, anyway, ignore that point if it's confusing to you. Let's just think about laminations equipped with measures. This has various advantages, one of which is it's equipped with a nice topology. It comes with the weak star topology on measures, which one has to think a little bit carefully about exactly how that interacts with the geometric structure. But this is a naturally topological space, and Thurston proved that it's in fact a very particular space. It's, well, let's see, if M is closed of genus G, for example, then this is just R to the 6G minus 6. So it's some kind of it's a finite dimensional space in particular. And while we are at it, we should also note that this space is isomorphic to the Teichmüller space of M, which is the space of all hyperbolic structures that we talked about before, up to some natural equivalence, up to isotopy. So this is the space that Teichmüller studied in a very different setting. He studied in the setting of complex analysis. Well, there are two things, right? These two statements.
Why does it turn out independent?
This is a great question. So the story that Thurston tells about this is that when he knew about Teichmüller space, and he also was interested in these objects, and he computed the dimension, and he saw the dimension, and I think his story is his head started buzzing when he saw that the dimension was the same. So obviously there has to be a reason. Okay, there's only so much I was going to say about this, but let me come back to this for a second, because I kind of wanted to explain line 1 in this list for a second. So what Thurston did was he proved, this is already showing you that these are relevant, right? In fact, okay, what Thurston showed was that the Teichmüller space has a natural compactification so a compactification means you take Teichmüller space, which looks like a cell, and include it in a compact space. That's what compactification is. So I should say what the added points are. The added points will be PML of S. So these are just ML modulo, well, maybe minus, there's a kind of the empty lamination, which we'll call 0, and then you mod out by multiplication by positive numbers. So if you once I put measures on, I can always multiply the measures by positive constants. So there's a natural multiplication by R plus. And if I mod out by that, the space I get left is a sphere. And so he produced compactification that looks like this, right? The Teichmüller space on the inside and the sphere of the correct dimension on the outside. And now I didn't say what the word natural means. So this whole thing admits an action, a natural action by the mapping class group of the manifold. This is just all homeomorphisms. Maybe we'll take orientation preserving up to isotopy. Is there a question? Oh, sorry. Yeah, I usually call it S. That's what happened. Let me stick with 1. Right. The punchline. Okay, there are actually this relates us to 2 different punchlines. But one punchline is that the sphere I didn't finish the sentence. Sorry. This whole picture, everything here admits an action by homeomorphisms. If you think about what we have, right? We have metrics on the manifold. If you apply a homeomorphism to a metric, you get, or a diffeomorphism, let's say, you get another metric. And so there's an action. And because the metrics are considered up to isotopy, then the homeomorphisms should be considered up to isotopy. And so there's an action of these homeomorphisms on the metrics. There's also an action on the laminations. We already saw this, essentially we saw this action because the laminations are kind of encoded by these pairs of endpoints, and any homeomorphism, the surface will also act on the circle at infinity. So the whole thing admits an action by this natural group, and the statement that it's natural is that this action is topologically good. It's an action by homeomorphisms. A priori, it could be a terrible action. So this action is a homeomorphic action. So the whole thing starts to behave in a way that looks a lot like, hyperbolic space with a group acting on hyperbolic space. There's a boundary, an interior, and so on. And so the laminations are here. They are encoding the asymptotic behavior. But I mean, it's asymptotic just because it's the compactification. When I go off to infinity in the Teichner space, I can converge to a point which somehow encodes something about the asymptotics of the sequence. That's what a compactification does. So that's the connection here. Maybe I want to say one thing about, let me say this without writing too much. I asked you to think about why are laminations the right thing and not these self-intersecting objects, which are usually called currents, like the things with self-intersections. Why don't they come up? Let me say just one tiny thing about that, which is that so these things, the set of all such things, all flow invariant closed subsets. Well, in fact, let's take all flow invariant measures on the unit tangent bundle. Let's call that, these are called the currents. That's just a name. Okay, so there's the space of all invariant measures, which is kind of a huge space. This is an infinite dimensional space. So what's special about, do this here. So PML of S is inside this space of all currents. So this is keep doing the S instead of the M. So this is some huge infinite dimensional space of invariant measures, and this is some manifold. And what's special about it, and I'll say, this was projectivized because I modded out by scaling. I should mod out by scaling here also. So here's a fact. PML is the smallest non-empty mapping class group invariant set in the space of all currents. One has to think about why that's true, but if you're looking for ways to prove that that's true, I will point out the following thing. If you take any closed curve on a surface, there's a special kind of homeomorphism that preserves this closed curve, namely a Dane twist. So you could take the self-homeomorphism that preserves the curve, and anything that crosses it gets twisted one time around, like that. Okay, so that map, which twists around this curve, it's called a Dane twist. It preserves this thing, and if you take anything else that crosses it, it twists it. If you repeat it, it twists many, many times, and in measure, it converges to the curve. So what's happening is that the closed curves, the closed non-self-intersecting curves, are fixed points in here of various elements of this group. And they kind of attract various parts of the space. And so if you had any invariant set, closed invariant set, did I say closed? Closed. I guess what I'm trying to say is if you had any invariant set under the mapping class group, it would have to contain all the simple curves. And if it contains all the simple curves, because there are so many simple curves, it turns out that the closure of the set of all simple curves is this set of measured laminations, projectivized measured laminations. So it somehow is forced on you to consider this when you're thinking about exactly this question. What should the boundary be? Well, the smallest thing it could be would be this. And that in fact is what it is. Was there a question?
The way, given the geometric structure, like the pointing pattern in space, the way you encode it using measured laminations, just by looking at all those curves, in that specific structure.
Wait, say that again.
Like, given the pointing pattern of space, how do you get a measured?
No. Given a point factor, I don't get a measured lamination. What I'm getting is I'm getting measured laminations up to scaling by going to infinity in the Teichmüller space. So I did not actually. I mean, it is possible to. There are some choices involved. You could actually identify by making various choices this space with this space, but that's not exactly what I'm doing. I'm identifying the spaces at infinity in some way.
You're saying it's like the boundary.
It's the boundary. Yeah, that's right. You should. What Thurston actually did was it wasn't literally this space, but it was something very close to it. And he essentially, I'm not really explaining this, but he sort of embedded inside here, he did two things. First of all, this is ML is embedded in the current space. So you should think of that as kind of a cone, because ML is just, we said it was Euclidean space equipped with this multiplication just by constants of the measures. And that, I don't quite know what it looks like in here, but I'll draw it as a cone, like this. I'm not proving anything, am I? I'm just drawing a picture. So ML is some kind of a cone inside the current space. And he embedded Teichmüller space also inside of here in some kind of more complicated looking surface. And they are asymptotic to each other in the same way as a hyperboloid is asymptotic to the cone that it spans. So this picture, one need to prove something, obviously, but there's a picture like this which explains how these two spaces meet at infinity. Okay. Okay, I didn't get very far in my little story. Especially, I didn't get to this. So I think I'll have to. This is actually the part that doesn't. These two relate to each other. Somehow the families of deformations are this Teichmüller space. And I didn't explain how a lamination can help you to deform a surface. Let me say one thing about that, actually. Let me say a tiny thing about that, which is that there are many ways in which a lamination can allow you to deform the hyperbolic metric. The most simple one, I almost drew it here already. Erase this. I have like 30 seconds left. Is that right? 5 minutes. Oh, awesome. Okay. Yeah. So you could take a surface, a hyperbolic surface, and you could pick a closed geodesic, and you could deform the metric in the following way. You could cut the surface. Let me place some stuff on the surface. Maybe I'll spill some blue ink on the surface. And then I'm going to cut along the white curve and then re-glue it. This happens all the time, right? If you cut along something and then you re-glue, you might not re-glue by the identity. You might have. So if I did that, if I re-glued, if I was careful to, when I cut, I get two circles that are both isometric to each other, and I want to glue them back by an isometry, but I might be off by a twist, right? So if I glue it, carelessly, I might get a picture that looks like this, right? And so this object produces a new hyperbolic metric on the surface. It's not the same hyperbolic structure it was before. This is called, this is a special case of what's called an earthquake. So that determines a flow on the space of structures. I can kind of keep going, keep twisting and twisting, and I get a family of different hyperbolic structures which are somehow controlled by this initial curve I chose and some time parameter. So that's called an earthquake. today is not a good day to talk about earthquakes, actually. So sorry about that. Okay, so that's one of many ways that you can use closed. Well, it's important that it's a simple closed curve, because if I did this with a curve that had self-intersections, it wouldn't be clear what to do. Like, there's not an obvious way to do this operation when there's this picture. So I really need no self-intersections to make this work. And then it turns out, this is one of still Thurston's constructions, that you can do this not just when it's a closed curve, but when it's a lamination. So a general lamination, its leaves are no longer closed. They might be infinite leaves that recur all over the surface, and you can still somehow cut and reglue and get this deformation. So that is one of the ways also, you were trying to ask me about this, that you relate the interior of Teichmüller space to something associated to lamination. So that's these two, and maybe this one will come up in the second lecture, so I'll stop here. Okay.
Something that's going to be geodesic by the structure of X is not going to be geodesic by the structure of Y.
Yeah, that's right. A geodesic, right.
Yeah, so is there, so can you characterize among the laminations and as the topological spaces, the ones that come from any Riemannian structure? So is it all of them, or if not, what do they have special properties?
Yeah, you can, it's actually, yeah, you can. So there's three things you have to rule out. Okay, so here are things. So you're saying, what if I just have a topological lamination? And then how do I know that it might be one of these geodesic ones, right? So here are three things that I have to disallow. One of them is, if there's a leaf that's a closed leaf which bounds a disk, then such a thing cannot be a geodesic, because it bounds a disk, it would lift upstairs to a curve that bounds a disk, and it couldn't be a geodesic. So the leaves cannot be homotopically trivial in this way, okay? And then the second thing I'm not allowed to do is to have a leaf which, suppose I have a leaf which bounds a region that looks like this. So it's still a disk, but now it has kind of an asymptotic end, which is now, so this picture, the leaf has two ends, right? This one and this one, but they are asymptotic. As you follow them around, they just get closer and closer. So there's some picture like this. I'm not allowed to have, so the reason I'm not allowed to have this is that if I were to lift this to the universal cover, it would produce some picture like this, and no geodesic can do that. This one would produce a picture like this, that geodesic can't do that either. And then the last thing I'm not allowed to do, is to have two leaves which bound a disk between them and have ends that are asymptotic somehow, that kind of travel together. So here's another. So this thing is called, the disk, this is called a monogon, because it's it's like a polygon with one vertex. This is a bigon. And the reason I'm not allowed to have this one is that if I drew them if I lifted this universal cover, I would have a picture that looks like this. And the geodesics would become the same if I pulled them tight. So it's a theorem that if I don't have any of these things, then it is in fact isotopic to a geodesic. That makes it a geodesic lamination. Yeah, that's right. Yeah.
I think in terms of like potential Nielsen coordinates, so like the earthquake maps been into twist coordinates.
Right.
If I look at the closed geodesics, how do I get like changing the length of the closed geodesics from like must be some kind of non-closed lamination? Is it possible?
Oh, this is a great question. Yeah. I mean, there's not a unique way to do it, but there are various nice ways to do it. So you're asking, okay, let me, I didn't say Frenchel-Nielsen in this talk, but I will. You're thinking about this, that if I think somebody asked, why is the Teichmann space, in fact, R to the 6G minus 6? And that one of the nice proofs of this is to cut the surface up into pants. So this is a maximal collection of disjoint simple curves, disjoint non-parallel essential simple curves. And it turns out that if I want to know what the hyperbolic metric on the surface is, I can uniquely determine it by measuring the lengths of the three geodesics and the twisting parameter for gluing each of them together, right? And changing the twisting parameter is exactly what we talked about before, is the earthquakes. And you're asking, is there a nice way to shrink this thing? So there is a nice way to shrink this thing. Let's see. We're running out of time. Let me draw. Okay. I should draw you one lamination that isn't trivial, right? So let's draw one lamination which. Let me see if I can do this in 1 minute. So here's one of these pairs of pants that's bounded by these three curves, and here's a fun lamination you can draw. I'm gonna draw. Let's see. Which way do I want to do this? Okay. So here's a geodesic. I can take a geodesic which in one direction spirals around this boundary, and in the other direction, I have to decide which way, but I'm trying to make it symmetric. So, okay, it doesn't matter. Let's just do this one. So here's a geodesic that spirals around the two boundary components. There's three more I can draw that are all disjoint. There's this one. There's maybe I'll draw this one. And then there's this one. Okay, does everybody see what I've drawn? So here's for example, here's a triangle whose three ends spiral around the three boundary components. And in the complement, it's a little hard to see. The complement of this triangle is also a triangle. And so I can draw this pair of pants as the identification of two triangles together along their boundaries. Each triangle by itself lifts to just an ideal triangle in the hyperbolic plane. Up to isometries of the hyperbolic plane, all ideal triangles are isometric. So the only data that's interesting here is what is the gluing parameter along these edges. Okay, I think I shouldn't do the details, but my claim is the geodesic length of this curve can be read off as a certain sum of the gluing parameters of the edges that spiral on the edge. So one way to kind of change the length of this edge is to do a certain kind of sliding deformation for these gluing maps. So I can turn the squeezing deformation of this geodesic into a sliding deformation on the triangles that make up the thing. So that's one way to talk about it. But you can also just, well, there are others also. Okay. Yeah. All right. This is the proof that Teichmann space is the dimension I claimed. There are the number of curves in this diagram is always 3G minus 3. And there's a length parameter and a twist parameter for each curve, and that gives you the 6G minus 6. So this is what's called the Frenchel-Nielsen coordinates. Okay.
So let's think